I would now like to calculate the electric field for another geometry, which is an infinite wire plus lambda. So this with a uniform charge density, charge per unit length, lambda. And I would like to consider what is the electric field outside the wire. Now, I'll just do it below, but the same argument will apply above. I want to consider, because this wire is infinite, just like on the plane, I can take an element of the wire, and I get dE1. And because the wire is infinite, there always will be another pair, another element, dQ2, exactly equidistant from the perpendicular bisector. And this will give us dE2. And when we add these together, we get the electric field of this pair. And I can divide the whole infinite wire pairwise. And that concludes that the electric field for this infinite wire is pointing away from the wire. So it's the same on the top if the wire is positively charged. So this gives me an idea about the field. And if I were to take a surface that's equidistant from the center of the wire, along this surface, everywhere, the electric field will have the same magnitude. And that will show me how to do the Gaussian law calculation. So now let's choose our Gaussian surface. So we have plus lambda. Here's our wire. What I want to choose is a Gaussian surface that is a cylinder that surrounds the wire. And the charge enclosed is here, inside this cylinder. Now, unlike the planar geometry, because the E field is pointing away from the wire, there's only going to be flux on the body of the cylinder. On the end sides, call that dE1, the electric field here is tangent to the surface, so there's no flux through the end caps. This is exactly opposite the planar case. Now, let's choose some parameters. Let's call the radius of the Gaussian surface r, and that will be our variable. And we'll call this the length L. Notice that I don't want to choose an infinite Gaussian surface because the charge enclosed would be infinite. So now we're ready. We have the flux is equal to the charge enclosed over epsilon naught. And now, what is the flux? It's just the E times the area of the body of the cylinder. The cylinder has radius r and length L. So the area of the body is circumference times length. So that's where our Gaussian parameters come in, r and L. And the charge enclosed, well, lambda is the charge per unit length. We have a length L of our Gaussian surface. So this is just lambda times L over epsilon naught. And when we set these two quantities equal, we see that the electric field is given by lambda over 2 pi epsilon naught. And I'll separate out the 1 over r part. So it makes sense that because of the infinite length of the wire, that our answer shouldn't depend on how long the Gaussian surface is. But it does make sense that it will depend on the parameter r. And notice, unlike a point charge, the field of a wire drops off like 1 over r. Well, how do we express this vectorially? We'll choose a cylindrical radially outward vector. So on both sides, the r hat points away from the axis of symmetry. And so we can write this as an electric field like that. And there is the electric field for an infinite wire, one of our basic examples of the application of Gauss's law.